Hello students, welcome to IMS GATE Academy. Myself, I am Dr. Vijaya Kumar. I am going to teach you foundation course of engineering mechanics. Alright guys, right. Now, in the foundation course, we have discussed statics as well as the dynamics also. And in the statics, we have seen that particles, dynamics of particles, and also now we are at the dynamics of the particle, engineering mechanics, dynamics of the rigid bodies we are discussing. Okay, right now. So what is dynamics actually? Dynamics, we have already discussed that dynamics is nothing but study the effects of forces and study the effects of forces on the given body, study the effects of forces when the body is in motion, right? How many types of motions do we have when the body is in motion? Okay, right. Now types of motion, as already we have discussed this in the first class. However, I just summarize that types of motions. Types of motions. As we have already discussed that there are three types of motions when a body, right. Now first one is a translation motion. First one is the translation motion, right. Second one is the rotation motion. Rotation motion, right. Fourth one is the general motion. Fourth one is the general motion. Isn't it guys, right? Now, so translation motion we indicate with T and rotation motion indicate with R. Now general motion is a combination of rotation and as well as the translation motion. Clear everybody? I hope everybody understand. Translation is now again translation is further divided into two categories. Okay, so first one is the rectilinear motion. First one is the rectilinear motion, right. Second one is the curvilinear motion. Curvilinear motion. So when the body, when we are studying the dynamics, we need to study the motions of the body, that is translation, rotation and general motion, right. So again translation motion is divided into two major categories, that one is the rectilinear motion as well as the curvilinear motion. Guys, as we have already discussed that this we have already initiated and elaborated that. Now when you are studying the translation motion, then the body considered as a particle, right. When you study the translation motion, the body considered as a particle. So particle is nothing but the size and shape of the body will not affect the motion. All right. Now here, now studying the rotation and also general motion is come under dynamics of rigid body. Okay, studying the rotation motion and general motion is come under dynamics of rigid body. Dynamics of rigid body. Right. Dynamics of rigid body, isn't it guys, right. Now when you are studying the translation motion, then the body considered as a particle. Now if you study the rotation motion and general motion, the body has to be considered as a rigid body. So we have already discussed that what is rigid body. A rigid body is nothing but it's a body, the size and shape of the body affects the motion of the object or affects the motion of object, then it is considered as a rigid body. All right. Particle means a small part in the body. But so if the size and shape of the body not affect the motion of the body, then it is considered as a particle. Clear everybody? I hope everybody understand, right. Now we are studying currently yesterday's session. Yesterday we had been discussed about rotation motion of rigid bodies, right. Now dynamics of rigid bodies again divide into two categories. One is kinematics of rigid body and dynamics of rigid body, right. Sorry, kinematics of rigid body and kinetics of rigid body. Okay, right. Now let's move for dynamics of rigid body. Dynamics of rigid body again further classified into two categories. That is, first one is the right. Now here first one is the kinematics of rigid body, kinematics of rigid body, right? Next, kinetics of rigid body, kinetics of rigid body, isn't it, guys? Kinetics of a rigid body. All right. So I hope everybody understand this. We already differentiate that what is the kinematics and what is the kinetics. Kinematics is nothing but, so whenever you want to create motion on the body, you need to apply force, right? So now here cause for the motion is force, right? Now if you are not considering the force and if you study the rigid body motion variables, that is come under kinematics, right? We are neglecting the force which cause the motion, is come under kinematics of rigid body. Now in the kinematics of rigid body, right, in the kinematics of rigid body, we will study the motion variables without considering the forces. All right. Now next is kinetics of rigid body. Here we consider the force which cause for the motion, right? And we will study the again motion variables such as, motion variables or displacement, velocity and acceleration and time. If you study, that is come under kinetics of rigid body, right? Kinematics of rigid body particles, that means rotational motion we have seen yesterday, right? In rotational motion, kinematics of rigid body, rotational motion we have seen, right? Now we will continue with the same, right? Now rotational motion, rotational motion, rotational motion. Yes guys, isn't it? Rotational motion. So now in the rotational motion, when the body is it rotate about its right. Now I am taking a body. Oh, I'm sorry. I am considering a body, right, which is hinged at this end, which is hinged at this end, right, hinged at this end, and we are taking this as a 0, right. Now after some time, after t time, the body right. Now the body is rotates about its axis, right, about the O point, right. Now the angle between these two is a theta, isn't it, guys? The angle between these two is a theta. All right. Right. Now this is the initial position. This is a initial position. Right. Now this is a final position. This is a final position, right. Now if I apply moment at this, then what happen na? The body is rotate about O and it's make an angle theta degrees in t time. In t time, let's say that the time is in t time, right. Now here I am taking a two particles, right. So here I am taking two particles, right, particle 1 and here particle 2, right. Now after some time, if I rotate the body, then my particle 1 will reach over here, say that 1 dash. Now my particle 2 is reaches to 2 dash position. All right guys, right. Now if I join this, then right, like this. Now the particle moves like this and second particle is also moves like this. Now when the body is in rotation, right, now to study these motion variables, we have two types of motion variables in the rotation motion. When a body under pure rotation, so in order to study the motion variables, we have two types of motion variables, angular motion variables and linear motion variables. Clear everybody guys? Clear? I hope everybody understand. I hope everybody understand, right? Now this 2 is not visible properly. I'll write it. Right. Now this is a second point. It is a 2 dash position. Now it is a 1 dash position. All right. So now I am taking one particle on a body, and this body is rotate about the O point such that particle 1 reaches to 1 dash, particle 2 reaches to 2 dash. Clear everybody? I hope everybody understands. So to study the motion variables in pure rotation, the motion variables are two types, right? When a body under pure rotation, when a body under pure rotation, pure rotational motion, when a body under pure rotational motion, it have two types of variables. Two types of variables, isn't it, guys? Two types of variables. All right. Now, what are that variables? First one already we have discussed that, angular motion variables. Angular motion variables, right? So in angular motion variables, what we have, right? So we have angular acceleration, one minute, angular acceleration, right? Now, so that is we indicate with the theta, right? Next, angular velocity, say that is omega, right? Now, angular acceleration, oh my god, angular acceleration is 1 minute, guys, angular acceleration is alpha, right? Angular displacement is theta, right? These are the things we have discussed. All right, right. Now, so we have derived the formula for angular acceleration, angular velocity, and also angular displacement. We have solved yesterday last class. We have just go to the lecture number 15, so that we have derived the angular motion variables when the body is in pure rotation. When the body is in pure rotation, suppose say that this I am considering one body, right? So this body is hinged at this point, and if I apply moment over here, it is going to be rotate about point O. It is rotate about going to point O, right? In order to study the when the body is in pure rotation, in order to study the motion variables, we have two types of motion variables. What are that? One is angular motion variables, and second one is the linear motion variables. Angular motion variables we have studied last session, right? Now, angular displacement, angular velocity, angular acceleration, we have derived the formula, as well as we have solved some example problems yesterday session, right? Now, today's session is when the body is in pure rotational motion, how to study the linear motion variables, all right, right. Now, today's concept is, second one is linear motion variables, right? Now, when your body under pure rotation, clear everybody, guys? Clear everybody? Right. So, the linear motion variables also studied the approach of the angular motion variables. Suppose say that what is angular motion variables? T is a angular displacement. So now omega is the angular velocity, that is with respect to theta derived with respect to t, then we will get the angular velocity. Now, angular acceleration alpha is equal to, it is going to be a d omega by dt. Sorry, it is not theta. Right, it is going to be a d theta. Right. Now we can write this fellow as well. So, right, d of dt into dw, w is d theta by dt. Right. Now I can write my angular acceleration d square theta by dt square. Always, all right, we can write this fellow, dw by d theta into d theta by dt. Like that also we can write. Now d theta by dt is angular velocity and it is dw by d theta. So we can write angular velocity like this also, right? Now by using these formulae, by using these relations, we are going to study the linear motion variables. So first of all, first linear motion variable is displacement, linear displacement. First variable is linear displacement. Linear displacement. Right. Now generally first motion variable linear displacement, so that we indicate with a S. Thus we indicate with a S, linear displacement. Okay, first linear variable. Okay, so linear motion variable, first one. These are all angular motion variables: angular displacement, angular velocity, and angular acceleration. Right. So by using this approach, we are going to derive the linear motion variables. That is, the first one is the linear displacement. How to will write linear displacement, right? Suppose say that go for this body. What is the linear displacement of the first particle? What is the linear displacement of the first particle? All right, what is the linear displacement of a particle 1? Right, what is that linear displacement? Right, so this is what, one minute. Right, linear displacement of first particle 1, linear displacement is that, I just highlight with the yellow. Have a look on this. This is what na, linearly it moves like this. Right, now the white line, similar white line only, but I just wanted to highlight that. So this is what your linear displacement of particle 1 when the body is under pure rotation, when the body under the pure rotation. Clear everybody? Right. Now how to calculate this length? So this length we are calling it as a linear displacement of the particle 1 when the body is completely in rotational motion. Clear? Right. How to calculate this length? Right. Now let us write that particle 1 linear displacement. Right. I will write particle 1, 1 minute. Particle 1 linear displacement. Particle 1 linear displacement. Right, how can I write? Can I write it is the distance between the 1 dash, right? 1 dash, isn't it, guys? Right. Right. Now here 1 to 1 dash is the particle 1 linear displacement. It is the initial position, it is the final position. When I apply rotation motion to this body, whenever it is hinged at point O, then what happen na? It is going to be rotate about, like this, anti-clockwise, such that my particle 1 moves linearly to the 1 dash position. Right. Now this displacement we are calling it as a linear displacement of a particle 1 when the body is under the pure rotation. Clear? I hope everybody understand. Clear, guys? Right. Now how to calculate this? Right. Now can I write like this? Right. Now point from point O, the distance is like this, up to 1. Right. Say that is a O1 distance. O1 distance into theta, so that I will get 1 to 1 dash na, isn't it? Right. O1 distance into theta, so that I will get my linear displacement of particle 1. Yes, guys. Right. Now 1 dash. So now linear displacement 1 dash is equal to 1 dash is equal to, I can write it is O1 into theta. O1 into theta, right? Similarly, calculate particle 2 displacement, linear displacement. Particle 2 linear displacement. Particle 2 linear displacement. All right, particle 2 is linear displacement. Can I write my particle 2 linear displacement? You know, so 2 to 2 dash is my particle 2 linear displacement, right? So this distance, you know, this distance is my, you know, this distance 2 to 2 dash is my linear displacement of particle 2 when this body is under pure rotation motion. Okay, I hope everybody understand, right? Now let us write that. Right, now it is going to be a 2 2 dash, right? Can I write my 2 to 2 dash? Can I write my 2 to 2 dash is equal to, you know, 0 to 2 distance into, you know, 0 to 2 distance into theta, right? Now let us see that where is my 0 to 2 distance. I'll highlight this here with a red, right? Now I'll write it from here, O to 2 distance. So O to 2 distance into theta, so that I'll get my 2 2 dash linear displacement. All right. So 0 to 2 into theta, I'll get 2 2 dash second particle linear displacement. If I write 0 to 1 distance into theta, then I'll get my linear displacement like this. But here you need to observe one thing. For every particle, if you take any particle, here in the body I have considered particle 1 and particle 2. If I consider any particle 3 here, then for 3 also theta is same, isn't it, right? What I am trying to explain you here, every particle in the body, when it is in pure rotation, its angular displacement is same, theta is same, angular displacement is same, but linear displacement is different. Why? Because this distance is going to be changed. 0 to 1 is different, 0 to 2 is different, 0 to 3 is different, right? That is the reason why here what happened now, when the body is in rotational motion, angular displacement is theta is same for every particle, but linear displacement is going to be changed, right? Now commonly I'll write my linear displacement equation, right? Now commonly I'll write my equation for the linear displacement. Can I write my linear displacement, right? Can I write my linear displacement? S is equal to, you know, can I write it is R into theta, R into theta. So where R is the distance between the axis of rotation to the particle, axis of rotation to the particle, right? Now here R is equal to distance between, you know, axis of rotation to the particle, isn't it, guys? To the particle, right? Now theta is the angular displacement, as we know that. Angular displacement. Yes, guys? Hope you understand, right? Or we can say that it is the radial distance between from center of rotation to particle, okay? So radial distance between center of rotation to, see, this is what my center of rotation. So now R equal to the distance between the center of rotation to the particle, right? So this is going to be changed, for every particle, but theta remains same, right? Now here I can say that theta remains same for every particle, and R is going to be changed, so that if you want to calculate linear displacement, then you need to multiply your angular displacement with the R. Now what is R? It is the center of rotation to the particle or body distance. I hope everybody understand. Linear displacement can be calculated like this, right? Now here 0 to 2 is the R, 0 to 1 is the R. 0 to 1 distance is different, 0 to 2 distance is different, right? I hope everybody understand what is linear velocity, sorry, linear displacement, right? Right. Now let us move for linear velocity. Next variable, second motion variable is linear velocity. Linear velocity. Say V. Say V. Linear velocity V. What is the velocity definition? Rate of change in displacement with respect to time is called linear velocity, right? Rate of change in linear displacement is called linear velocity, right? Now I'll write the definition. Rate of change of, right, linear displacement with respect to time. With respect to time. With respect to time. Isn't it, guys? Right? Now, can I write my V is equal to, it is, ds by dt? Can I write rate of change of displacement with respect to time is called linear velocity, right? What is S? We have derived S R into theta, na? R into theta, right? Now here, so d into dt into R into theta. R into theta. Where R is a constant, it is not going to be changed with respect to time, right? So that means the radial distance from the point, center of point to the particle R is not going to be changed, but theta can be changed with respect to time, right? Now for that I'll write, oh my god, 1 minute, guys. Right. Now I'll write my velocity V is equal to, it is R into dt by d theta by dt, d theta by dt. All right, right. Now from here, d theta by dt is equal to, it is going to be a r dot, so angular velocity. So d theta by dt is equal to angular velocity, now that we have already discussed, right? Now this is how you are supposed to find the linear velocity, right? Right. Velocity is the vector quantity. Velocity is the vector quantity. So it is having certain magnitude as well as the direction, right? Now let us fix the direction of V. Let us fix the direction of V. How to fix the rotation of V, right? Now velocity is the vector quantity. Velocity is the vector quantity. It must have linear, sorry, it must have magnitude and direction. Magnitude and direction, right? Now let us understand how to fix the direction of V, right? Now for that I am taking a body. All right. Now this body is hinged about this point. This body is hinged about this point. Now if I apply a load over here and it is going to be rotate like this. So now I am considering a point, say point A, B we have taken. Now point P we will take. Right. Now if I join this point, right, if I join this point, right, my velocity at P particle, about this O point, it is exactly perpendicular to the radial distance. It is exactly perpendicular to the radial distance, right? It is exactly perpendicular to the radial distance, isn't it, guys? Right? The velocity of the particle in a rotating body, or if a body, see that I am considering it as a body, right, which is hinged at a point O, and if I apply certain force here, then about this O point, this body is going to be rotated. In this, I am selecting one point in this body, particle P, right? At particle P, how my linear velocity, right? How about my linear velocity direction? I would like to highlight that. Now my linear velocity, see that here, whatever the linear velocity we have derived, that linear velocity is exactly perpendicular to the radial distance of center of rotation to the particle, right? Center of particle to the rotation. Now this distance we call it as r, right? Now my velocity, linear velocity, is perpendicular to the radial distance between the axis of rotation to the particle. Now suppose in the same fashion, I am considering a particle Q here, right? So now I want to know the velocity direction at this particle when my body is under rotation, right? At P particle, my velocity direction, my linear velocity direction is in this, right? Now at when my body is rotating about O point, now I want to know that linear velocity at this point, right? Now very simple, again, right? Again you draw the linear distance, this, right? That is r again. So if I take it is rp, now it is going to be a rq, right? Now my velocity is exactly perpendicular to this vq, all right, like that. Okay, so now my linear velocity for a particular particle is perpendicular to its radial distance. Clear, everybody? I hope everybody understand how to fix the direction of velocity when the body is in under rotational motion, right? So in order to fix the linear velocity direction when your body under pure rotation, this is what the procedure. Clear, everybody? Right? Now if you want, I can write it is okay, right. Now this is my rotation path, like this it will come na, rotation path, right? I will write linear velocity direction is perpendicular to the radial distance or tangential to the path. So this is my rotation path na. Now this is exactly tangential to the path, okay, to the radial distance. Oh my god, 1 minute. Radial distance or tangent to the path. Clear, everybody, guys? I hope everybody understand. Now we have derived the formula for linear velocity, that is v into r into dt, right? Now here see, guys, linear velocity, rate of change of displacement. Now what is s? S is equal to r into theta. R is not going to be changed with respect to time, but theta is going to be changed with respect to time. That is why r I have taken out, and then d theta by dt. Now d theta by dt, angular displacement with respect of time, then angular velocity, right? So now linear velocity I wrote in terms of angular velocity. That's it, very simple. All right. Now let us move for angular acceleration. Third motion variable, angular acceleration. Oh my god, it is linear acceleration. We are talking about linear motion variables now. Linear acceleration, right? This linear acceleration we indicate with theta. Guys, what is the definition of acceleration? The rate of change of velocity with respect to time come under linear acceleration. That's we already know that. Yes, right. Now let us write that. Let me write that. The rate of change of linear velocity with respect to time right, with respect to time called linear acceleration. All right guys, done everybody. I hope everybody understand. Right. Now here I can write my acceleration is equal to, it is dv by dt, right, dv by dt. But before we are going to discuss about this, I would like to highlight one thing here. Right. Now let's go back to our diagram. When the body is in under pure rotation, right, when the body under pure rotation. So at this particular particle, I'll just erase this path. This path I'm going to erase, okay, in order to make sure that, right. Here at exactly particle 1, what is my initial velocity of the particle? Say that it is exactly perpendicular to this one and it is u1 we say, right, u1 you say, and its direction is perpendicular to the particle, okay, right. Now here at 1, what is the velocity? Now it reaches to the final velocity, say VA, and its direction is perpendicular to the axis of rotation. That means the radial distance, right. Now this is my radial distance and it is perpendicular to radial distance, right. Now this is perpendicular distance, right. Now here when the body under pure rotation, initially it is having velocity u1 and its direction is upward, right. When my body rotates in t time to the final position, then my velocity of particle 1 becomes final velocity and its direction is perpendicular to the particle, right. If you observe here clearly, very clearly, that what happened now, the magnitude and direction of velocity is going to be changed. From initial position is different, for final position is different. Yes guys, right. Initially when the body is at initial position, its velocity, the particle 1 velocity is u1 and its direction is perpendicular to the radial distance. Done. This is r and this is also r, right. Now when I rotate this body about this O point in t time, it reaches to final position. In the final position, its velocity is become u1 to, oh my god, it is not ua, it is u1, v1, final velocity na v1, it reaches to v1. Everybody okay, right. Now the direction of velocity for a particle 1 is initial position is different, final position is different, right. What I would like to conclude here, the velocity magnitude and direction is different for particle 1 when the body is in rotation, right. Now here magnitude of the velocity is changing, direction of the velocity is also changing. Clear everybody, right. Excuse me, right. Now here in this case, when the body is in pure rotation, then we have two components of linear accelerations. One component change the magnitude, another component cause for the change in direction of velocity. That is what my intention to tell you, right. Now here when the body is in rotation, the linear acceleration having two components, right. When your body is in pure rotation, right, when your body is in pure rotation, the linear acceleration, the linear acceleration is divided into sorry, two components, not a problem, two components, all right. Right, first one is tangential acceleration AT, that is a tangential acceleration, all right. Now tangential acceleration is the cause for change in magnitude of velocity, right. Actually the velocity change its direction, its magnitude when it is in pure, the body is in pure rotation, right. Now here tangential acceleration is the cause for change in the magnitude of the velocity, all right. So now here AT is the causes change in magnitude of velocity, right. So tangential acceleration is the cause for changing the magnitude of velocity, changing the magnitude of velocity with respect to time, clear everybody? I hope everybody understand, right. Now next is second component is that normal acceleration AN, normal acceleration, right. So this normal acceleration is the cause for change in the direction of velocity, is the cause for change in direction of velocity, change in direction of velocity with respect to time, all right. Change in direction of velocity with respect to time, okay, right. Now here let's fix the directions of AN and AT, because these are also vector quantities, na, right. Now here I am considering one body. In this body, so point O, at point O it is hinged, right. Now I am taking a particle over here, say this particle P, right, and this body is rotating about like this clockwise, right. Now I just join like this, okay. Now I say that it is a RP, right. Now my angular acceleration, my AT is exactly perpendicular to this particle as like velocity, right. This is what AT, that means tangential acceleration component. So this is same as like that, V. So the velocity at this particle is perpendicular to the particle and perpendicular to the perpendicular to the RP, or else it is tangent to the rotating path, right. Now similarly AT is also same, right. Now AN is going to be like this. AN is going to be towards the center of rotation. Now this is going to be a AN. Now it is towards the center of rotation. This is AN and this is AT. Obviously the resultant will be different, na. Now let's find the resultant. Now this fellow is a resultant of AN and AT. So that is called A, right. I can write my A is equal, all right. Right guys, right. Now let us find how to find out AT and AN, right. acceleration component at is equal to, it is dv by dt, dv by dt. What is v? What is v? So v is, v is r into w, r into w, right. Now d of dt into, r into w. R is a constant now, I'll take out, so that dw by dt. So dw by dt, so angular velocity with respect to time, if I differentiate, then I'll get angular acceleration. Now it is going to be a r into alpha, right, where alpha is the angular acceleration, angular acceleration, right. Right. Now similarly find out that an is the, it is going to be a v square by r, such that what is v square? R dot r omega whole square is divided by r, such that I am going to get it is omega square dot r. So my at is equal to, it is angular velocity into radial distance. Now this is my at. I'm sorry, here it is an, guys. It is going to be a an, normal component of acceleration and tangential component of acceleration, right, guys. I hope everybody understand. I hope everybody understand, right. Now here, so let's write all at once what we have derived so far, right. Linear displacement, yes, is equal to, how can we write? R dot theta. All right. Next, linear velocity, that is v is equal to, we have derived that r into w. Yes, guys, r into w, right. Now let's linear acceleration, that is equal to, 1 minute, it is going to be a that is equal to, it is at square plus an square under root. Done, right. From here I will write my at is equal to, it is r dot alpha, right. Now my an is equal to, it is going to be a omega square into r, right. So now this is what we have related. That means linear motion variables we have correlated with the angular motion variables. From the based on the angular motion variables, we are going to calculate the linear motion variables. That is why, see here, linear displacement I have written in terms of angular displacement and angular displacement into radial distance. Linear velocity, angular velocity into linear velocity equal to angular velocity into radial distance. Now linear acceleration I wrote in terms of angular acceleration, right, angular velocity. I hope everybody understand. Now in order to understand these things, let us solve one example problem. So that you will be perfect in that. All right. Now let us see that one problem. Have a look on this problem. Right. A wheel of, see, you try first, I will solve however I will solve. You try first, however I will solve that. right. Now let me read the problem. A wheel of 1.2 meter diameter starts from rest and is accelerate at a rate of 0.8 radian per second square, right. Find the linear velocity in meters per second, okay, of a point on its periphery after 5 seconds. Of a point on its periphery of find the linear velocity of a point on its periphery after 5 seconds, right. Now let me draw the flywheel. Right, this is what my flywheel, right. Now here it is hinged at the center, say O, and it is going to be starting from the rest and rotating, right, at an acceleration of angular acceleration is given, right, and also its wheel diameter is given, right. So wheel diameter is 1.2 meters, my radius is 0.6 meter, isn't it, guys? Now here at this point we need to find linear velocity on his periphery, na. So a flywheel is 1.2 diameter, starts from rest. It is starting to rotate from the rest position and is accelerate at a rate of 0.8 radians per second square. So it is going to be accelerate at a 0.8 radian per second square. Find the linear velocity in meters per second of a point on its periphery after 5 seconds. After it is starting from the rest, and after 5 seconds, we need to find its linear velocity on its periphery, right. So can I say my linear velocity at here? I will say my linear velocity at here is equal to, it is, can I say it is Vp, linear velocity at point P, right. What are the things are given? Let me write given data. Angular acceleration is given, na? Angular acceleration is given. Now I'll write it as, right, angular acceleration alpha is equal to 0.8 radian per second square. All right. Now, so what we have to do, right? Now t is equal to, given time is equal to, it is gonna be a 5 seconds. It is gonna be a 5 seconds, right? Now what else given? And here you need to remember angular velocity, right? Angular velocity, right? If you observe this, it start from rest. So initial angular velocity is 0. Initial angular velocity is 0 because it is starting from rest. Right? Now let me write initial angular velocity is W naught is 0. So that I will write my initial angular velocity is 0. Right? Now say that W is a final angular velocity. Final angular velocity. Yes, guys, final angular velocity. I hope everybody understand, right? Now here we know that acceleration we know, t we know, initial velocity we know, final velocity we know, right? Now from here I'll write an equation. Like this, right? Now here final velocity is equal to initial velocity into t. 1 minute. No. 1 minute, guys. I just correct this. Plus alpha into t. Like, V is equal to basic equation. U plus AT na for linearities. for linearities, right? From the linear I develop angular final velocity, angular initial velocity, angular acceleration alpha and t, and find the final angular velocity after t equal to 5 seconds, right? Now let me write that. 1 minute. Right. Now, so W we do not know, right? W naught is 0, right? 1 minute guys. W naught is 0 less, alpha is 0.8 and into t is 5 seconds, right? And now my angular velocity W I am going to get it is 4 radian per second. 4 radian per second. Yes, guys. Yes. Please do respond. Right. Now here I got angular velocity, right? After 5 seconds. Now I don't require angular velocity. In the problem they ask that, what they ask? Linear velocity we need to find, right? Now let me write linear velocity. Right, linear velocity, V is equal to what we have derived? R into W, na? We have derived R into W, right? Now here what is R? 0 point, flywheel diameter is 1.2 meters, but radius is 0.6, half of the diameter, na? So 0.6, now if we want I can write here, D is equal to 1.2 meter, then R is equal to 0.6 meter, you can write, right? Now here my R is equal to it is 0.6 meter into 4 radian per second, such that I am going to get it is, how much it is? 2.4 meter per second. 2.4 meter per second. This is my linear velocity. In order to find out the linear velocity, first I need to find out the angular velocity, and then by using my formula, what I have derived, see here, I'll write all at once, na? So linear velocity R into theta, linear displacement R into theta. Next, linear velocity V into R into W, V equal to R into W. So R and W, first W I need to find, and then if I multiply with the radial distance, so that I will get. Hope you understand, right? Now similarly the same principle I have applied for my problem solution. When it is start from rest, then my W not equal to 0, right? Now linear velocity will come in meters per second. I hope everybody understand this concept. That means linear variables, and here we have studied when the body is in pure rotation, we have studied that angular motion variables and linear motion variables. That is all about kinematics of rigid bodies. Okay, right. Now here let us go for introducing our stakeholders. Right. Now here see guys, on the screen you are going to see that GATE toppers in 2023 success stories, right? Now, so if you are enrolled with the IMS GATE Academy, now you may fit into in this frame. Here I would like to convey one thing, guys. If you want to so interact with this session, if you like this session, and also explore to your friends. Okay, now if you want to enroll to with the IMS GATE Academy, then so some numbers are floating in the screen. You just call to them, they will counsel you, motivate you, and so make you to perfect in order to crack the GATE 24-25. All right. Now this particularly the foundation courses are designed by the IMS GATE Academy in order to enhance in order to inject the basics of subjects to the students, right? So in the next week we are starting manufacturing basics foundation course also, right? So myself only, Dr. Vijaya Kumar, is going to be teach you that, and some foundation courses for different modules are also going on, and you just subscribe our channel so that you will get updates every day, right? Now let me introduce that. So All India rank 3rd for mechanical branch in GATE 2023, right? Now All India rank in instrumentation, All India rank 4 in computer science, All India 4 rank in production and industrial, All India rank in mechanical 7th rank, now All India 9th rank of mechanical, All India rank of production and industrial is 10, now All India rank of 17 in ECE, All India rank of 15 in EEE, All India rank of civil engineering 19. So there are so many number of ranks below the 100. So here I just placed the top 20 only. Okay, right? Now here what I'm trying to explain you guys. So enroll with the IMS GATE Academy such that you will enjoy the content, and you will interact with the faculty, best faculty in India, which are having higher experience and good qualification also. All right. Now let us see what course features we are providing. If you are enrolled with the IMS GATE Academy, we'll train you in such a way that to crack the GATE exam in 24-25. All right. Now see here, if you are enrolled with us, then the course features are 800 plus live sessions and 130 plus online test series, right? Now 22 to 30 theory and exercise books. Theory and exercise book. Theory books are equipped with the conceptual explanation, all right, conceptual explanation, and some solved examples. So exercise book is completely dedicated to the problem solutions only, all objective questions with the level equipped with the level 1, level 2, level 3 also. All right. Next, 12 1-to-1 personalized mentorship session, right? Now what personalized mentorship means, those students are preparing very well, they're doing very hard work, but there is a possibility that some people before the exam they may get fear and nervous. In order to enhance the confidence levels of the students, then we are conducting 12 1-to-1 personalized mentorship sessions with the faculty, right? So you may book the faculty such that faculty will come online and teach you in such a way that how to prepare for the GATE exam and what are the strategies you need to follow, how many hours you have to study. All these things are going to be explained by the mentor to the student. That is what the 12 1-to-1 personalized sessions, right? And apart from academics, the strategies and weightages, all these things we can discuss in the 1-to-1 personalized mentorship. And we will provide you revision sessions, right? Now admissions are going on, and you may contact with the following numbers such that our team will come and counseling you and give you the best features what I have explained. They will explain you and counseling you related to the course, right? So now thank you very much for your patient listen. This is what about dynamics of rigid bodies we have covered today, and thanks for the patient listen. Thank you.